Okay, second video on alternative resource inputs, and I think maybe a ninth video on the Solow mechanisms. So remember, the basic Solow mechanism, the second one, is like we can shift between resources. If resource 1 starts getting scarce and the price goes up, maybe we can shift to resource 2. The more sophisticated version is like, okay, and that shift can be helped by directed technological change. We can shift investment resources into the productivity of resource 2. And an extreme version of the DTC model said actually we're going to like move completely from one resource to another. But in fact, if we've been using one resource and not the other for a long time, then it's going to be very hard to shift because we're going to get locked in. And that really didn't fit the data very well. It turns out that a much simpler model without any DTC and just with a fixed substitutability between the inputs does a much better job of matching the data. We're just going to look at that now. So we've had if we have Cobb-Douglas, we have y is ALL to 1 minus alpha, ARR to the alpha, and we can set up the final good producers profit maximization problem, and we get these fixed shares. WRR is alpha y. But what if we stick with the Cobb-Douglas and we have a fixed share of the resource in the final goods sector, but we have this this resource sector here, which putting things together, and here in here we have the CES. So we go back to this CES idea, but now without any directed technological change. Okay, so how does that play out? So we've got, and I'm not sure we're going to use these gammas, so let me see. Okay, we are going to use the gammas, so we'll put the gammas in. So we're in that black box of the resource sector, and we're putting together the overall resource, and it's a CES function of resource C, which is gamma C ACT XCT to the epsilon plus gamma D ADT X DT to the epsilon all to the 1 over epsilon, and they're good substitutes, so epsilon is greater than 0. And now, just to emphasize that we don't have any directed technological change, so we just say ACT and ADT, they're just fixed and equal. So the difference between these two is actually in the gammas, so that's why we're bringing in the gammas. And slightly right, AR is 1. Okay, yeah, right, AR is 1, so then YT becomes AL or ALT, LT, but sorry, ALT is also just AT. So YT is AT, LT to the 1 minus alpha. Then we had ART, RT to the alpha, but we're just saying ART is 1, so it's RT to the alpha. That's that one. And then we've got RT is this, but we can take this A out here, A to the epsilon, A to the epsilon. Then we can take it all the way out, and it's like A to the epsilon. Oh, if we can take it, we can go like this, A to the epsilon times that, and then we can change these brackets to be like that. Okay, and then we wipe that a to the epsilon and that a to the epsilon. So we can rewrite like this: a to the epsilon times, in square brackets, this, all to the 1 over epsilon. And then we've got a to the epsilon to the 1 over epsilon. So we can write it as a square brackets, this lot, to the 1 over epsilon. Gamma c xc to the epsilon, gamma d xd to the epsilon to the 1 over epsilon. I've dropped the t's. And consumption, if we think about the overall picture that we looked before, it's y minus big X, or y minus wc xc minus wd xd. Let's see if we can see that in this picture. Okay, so we haven't actually specified here, we've just got a big X, but we can think of these inputs into these two sectors being wd xd wc xc, if we're calling these clean and dirty. Okie doke. Right. So, what can we do with this? Well, we can set up a profit maximization function of one of these producers in the black box. The output is R, and the inputs are XC. Sorry, I need a drink. I don't have one. I'll see if I can keep going. The inputs are XC and XD, prices WC and WD. Okay, so the profits are just revenue, which is WR times R, and R of course is given by that, minus WC XC minus WD XD. Okay, and then if we take first order conditions, if we take the first order condition in R, for instance, sorry, not in R, in XC, then again, sorry, here we have it. Yeah, here is R. A better expression for R. Then again, we end up with 1 over epsilon times everything, 1 over epsilon minus 1, which is 1 minus epsilon over epsilon, which is just R over A to the 1 minus epsilon. So WR, that's exogenous, and then we've got R over A to the 1 minus epsilon. Then we go inside, and we've got epsilon, gamma C xc to the epsilon over xc. But the epsilon cancels out with that 1 over epsilon. So we have gamma C xc to the epsilon over xc equals, or minus wc, when we differentiate with respect to xc, equals naught. So we can say minus wc equals naught, but then we can take that over and say equals wc, and we can take that up, and we end up with that, okay, where that's gone. So wr, r over a to the 1 minus epsilon, xc, gamma c xc to the epsilon equals wc xc. And by symmetry, we have wr, r over a to the 1 minus epsilon, gamma d xd to the epsilon is wd xd. And when we put this all together, we end up with well, yeah, after a little bit of manipulation, we end up with, and I'm not going to take you through that, it's WCXC over WDXD equals gamma C over WC divided by gamma D over WD, all to the epsilon over 1 minus epsilon. So if we've got an exogenous, we've got these fixed parameters about like how much do we like these different inputs, and then we have this exogenous development of the relative prices of the inputs. This tells us, depending on epsilon, this tells us how the factor shares of the inputs should develop. So if epsilon is very close to 1, then we've got 1 over something very small. This is very large. So then the factor shares will change hugely, because this is raised to a very large power when these relative prices change a bit. So if WC goes down a bit and this is very large, then the factor share of C will go up hugely, right? So they're very good substitutes. C gets a bit cheaper, we'll use loads more C. But if they're not such good substitutes, imagine epsilon is a half, then this is a half over 1 minus a half. That's a half over a half, that's just 1. Then it's not very sensitive at all, right? Okay, so this implies that the resource that is cheaper per efficiency unit takes the larger factor share. The advantage is bigger, the higher is the substitutability between the resources. Okay. Let me just pause and see what I'm doing here. Okay, we've really done the interesting bit. I think in the interest of time, I'm not going to take you through this next bit, or I'm not going to go through the math here on paper. But basically, we've got these two equations, right? And they pop up again here. So these are the equations for what we spend on input C and what we spend on input D as a function of a bunch of stuff. And we want to know what happens to the price of R, what's coming out of the black box. Remember, XC and XD are coming in and R is coming out. What happens to the price of R? It depends in given perfect markets, it depends on unit cost, which is the total cost of inputs divided by the total quantity. The total cost of inputs is WCXC plus WDXD, which is this, which we can then write as this. Right, this. So WR is that, which is just this again. WRR, we know from the final goods sector, the Cobb-Douglas, WRR is just alpha Y. So WR is alpha times Y over R, which is this. So we have two expressions for WR, and we can put this equal to this and get this. So this tells us that R is AL, which is effective labor, times this thing, which is a function of the prices WC and WD. Okay, so what is that all for? We've got expressions, we've got an expression for the relative factor shares of the two inputs, and we've got relative to each other, And now we've got an expression for the total quantity of resource and also the total expenditure on the resource, because we know WR in terms of the prices of these two resource inputs. Okay, so what we can do now is say we've got two resource inputs and we've got price trends for them. We can write a little model in MATLAB or write a little simulation program and get it to spit out, for given epsilon, what we should be spending on the two resources, and how, for given alpha and so on for our overall model, how GDP should be developing, how the overall resource expenditure should be developing, and so on. And we can play around with parameters and see if we can get the model to fit the data. Okay, and it turns out that in lots of cases the model can do a pretty good job. Okay, so this is data on, we've got input data on the coal price, the dotted line here, and the oil price, sorry, the continuous line here. Okay, coal price, that's our input, and then we've chosen some parameters, and this is our global product data, and then we've chosen some parameters to get predicted, and we've also got oil expenditure and coal expenditure in the data. So in the left-hand figure we see observed prices and expenditures, with expenditures compared to global product. Okay. In the middle figure we see observed total expenditure on coal and oil compared to the model prediction. So this is total R, if you like, or WR. It's like WR, what were they called again? No, WCXC plus WDXD. Okay, so for the parameters we've chosen, the dashed line is what the model says given these prices, and the continuous line is the observed expenditure. That's basically this one again, isn't it? Oh no, it's the sum of coal and oil. And in the third one we see the observed factor share of coal and oil relative to each other and the modeled shares. Okay, the fluctuations tell you the model is not dealing with very short run price fluctuations well, which is exactly what we expect, because the model is not capturing the sort of inelasticities in the market in the short run. But in the long run it is capturing very well, or pretty well. It is predicting the change in the shares as the relative prices change. So basically the long run trend here until the end, when things go off because the model just hasn't been able to keep up, but we've got a long run trend over like 100 years with oil getting cheaper compared to coal and taking a bigger and bigger share of the market. Okay, and the parameters are alpha is 0.02, so that's 2% share for energy. Gamma C over gamma D is 0.55, so coal is intrinsically not as good as oil. We sort of, everything else equal, we prefer oil. And epsilon is 0.76, so they're pretty good substitutes. This is the same thing for iron and aluminium. I'm not going to take you through it, but again we see that the model is doing a great job. Now, aluminium is much more valuable than iron, everything else equal. Okay, the factor share of the iron and aluminium combined is very small. Okay, it's what would it be? That's 0.2% of global GDP roughly is spent on iron and aluminium. And the elasticity is 0.55, so we're not quite as happy to substitute iron for aluminium and vice versa as we were to substitute coal and oil. But they're still pretty good substitutes. So basically we can get a long way with a much simpler model without any directed technological change, explicitly modeled. At least for explaining the long run, but that model completely fails to capture short run fluctuations, which a model with DTC but with links between knowledge stocks could potentially capture both short run fluctuations and the long run. Okay, that is that on the simple model.